Hello everyone, welcome back to my another video. This time I'll introduce you with a facial recognition in Python in a real time run on our CPU. Well, the real time. Real time means when our inference achieves around 20 to 30 frames per second. So our goal is to achieve something like that. Well, you may ask, what is facial recognition? And I think we can separate this into three different steps. So it's face detection or localization in a frame, then face feature extraction. This means that we, from these faces, extract some kind of vector. And at the third step, we use some kind of math to measure the distance of this vector between our saved vectors in our disk, RAM, memory, doesn't matter where, but we will simply need to measure the distance between known persons with that face. There's many ways how we can implement either face detection or this face feature extraction, but I, in this tutorial, chose to use one of the most popular Google released MediaPipe face detectors that I covered already in my, I think, first tutorial. And if you want to see how to run it in real time on your webcam stream, on your image, or even video, you can check this tutorial. The link is in the video description. And the second, I'll use a FaceNet. This is a Facebook released face identification model that simply extracts the vector from our faces. But let's tackle this problem one step at a time. And here I'm not going to go very deep into the details because this tutorial would be endless, and if you want to get more details about that, there's plenty information online, there's a lot of theory and so on, so you can Google it. So first, let's talk about face detection or face localization, so-called. Even thought that I already covered this in my first tutorial. If you want to get deeper, you can cover it, but continuing this tutorial, well, face detector is one of the most popular techniques used nowadays. You probably during 10 years saw how social networks use it. For example, on a Facebook, when you upload a photo, you can see that Facebook automatically tags faces. You simply need to add tag people who are in there. It's even possible that Facebook recommends who is there according to their face. This is actually how facial recognition implemented online. Also, our smartphones use the camera, and there is a facial detection technique. So, for example, when you are making a photo, it makes sure that our faces are focused properly before making a capture of it. So this is only two examples where it's used, but there's plenty of solutions where it can be implemented. And after, of course, completing this tutorial, you'll be able to implement it whenever you want. I chose to use MediaPipe, but also I covered a few other different most popular face detectors as MTCNN face detector, DLib, MediaPipe, pure convolutional neural networks, and it seems MediaPipe is one of the lightweights, one of the easiest to implement out of the box, and MTCNN is also very accurate and really quick face detector, of course, if we convert this to ONNX, because TensorFlow is not the best way to use inference on our everyday use. Okay, let's continue with our face feature extractor. I chose to use FaceNet. And FaceNet was released by Google researchers in 2015. And what this does? Well, actually, as input, we feed our human faces, and as an output, it gives us 128 numbers vector. Really hard to tell what does it mean, this vector, but we know that there is a meaning for that. For example, it's like a hashed distance between our eyes, between our nose and lips, between our ears, and etc. There will be a lot of information there hashed. And when we see this vector, it's impossible to tell us what is there. And how actually we use this vector? Well, nowadays, if you're not new to machine learning, we always use this technique for in object detection. For example, when we are tracking our objects between our different video frames, because there is a special tracking algorithm applied, and there's a problem usually when we have two frames, how we capture the same object from first frame to another frame. Well, because when you use object detection, there is only a bounding box around, and simply there is a similarity algorithms applied, so that also converts. For example, there is a car, and they creates a vector of that car from first frame, and they takes a vector from second frame and calculates the distance between these two vectors. The lower the distance, the more similar these objects are. For example, 1.01. This means the same car. So similar is here. When we want to identify the people in a frame of the what is the first person there, what's the name of it, or etc. We should have some kind of photo of the person we want to identify. For example, if I can have my own face somewhere on disk, I push my face through this FaceNet algorithm and I receive this 128 vector. I save it somewhere, and next time when I can run, for example, this FaceNet on real web camera stream, and it gives us every frame, it gives us a vector. So I use a cosine distance or Euclidean distance to measure the distance of my saved face and the new face, and I check what is the values. Usually lower the value, more similar the face will be, and this is how it works. But you might ask, okay, we have this algorithm, but how would I need to train this by myself if we would like to? Well, it's pretty tough task that I'm not covering here, and I will not give you algorithm to do so. But usually, as I said, there's plenty of information online and you can find it. But the idea is that you should have several thousands of different faces of people, and one person should have at least two faces on your training dataset. And the idea is that you randomly pick a face and one face, and you randomly pick a second face of the same person, exactly the same person, and you feed it through the algorithm, and you receive these two vectors. At first, these vectors are pretty random numbers, and they don't tell us anything, and there is no use of it. But then we pick randomly a different face, mostly different from, for example, for me, and we have two different faces, and we know that one vector should be as low as possible and another should be as high as possible because there is a different person. In this case, our algorithm goal is to increase this difference and minimize the difference between same faces. Well, and we do this, iterate over and over and over, and we simply achieve our goal where there's no more improvement can made to this neural network. And at this stage, we know that our network is trained and we can use it whenever we want. But it's enough of theory. I believe it's enough for you, and you are here because you want to get the code, you want to test this. It's way more fun to test this around, but nowadays everything, always I say that it's important to know how it works, at least the background, not the math side. And I give you a short explanation of that. And right now, let's cover my FaceNet. I hope you're not the first time here on this tutorial series, and I hope you had time to check my previous few tutorials. And because here I created an object that is engine, and for this engine is responsible for processing different tasks, and here I can feed the image, I can feed the video, I can feed the real-time camera stream from my webcam, And here, as you can see, I apply many objects, and there is a segmentation module, FaceNet module, and it might be face detection module as I used before, and etc. It's up to us what we're gonna use. And idea here is that these objects are initialized somewhere, and they have a call function where we feed our frame and they do their thing around that. But right now there's a little different object, this FaceNet, but I already created it, and let's cover it. And the idea here that face recognition must have face detector. So instead feeding face detector to my engine, I created that I'll feed this face detection to my FaceNet object, as you can see, and it will simply run the detector and will detect the faces. Next, I need this FaceNet model, and then I need an archos. It is folder called faces. There is a threshold, and whether we want to use CPU or not. It's true, false. Of course, there is more stuff here that we can change, but let's do it with step by step. Okay, let's go to FaceNet. And as is all here, there's a color, thickness. This is especially for drawing things of our identification. So here is our model, FaceNet. I'll not cover it here, but if you go to the architecture, there is a whole architecture of this FaceNet that I copied it from here. And if you want to get more details about that, you should go into this link. Read about this. Of course, there's weights you can download, and etc. There's many stuff here, but idea is not that you came here to cover the line by line of this TensorFlow model. So next, I use convert to OpenNX. So here I simply showed you a link where you can simply download this FaceNet Keras weights H5 file. And the idea here that you download it, you put it into the models folder, and the models folder after conversion appear a new file, facenet.onNX. And here I initialize the architecture, load the weights, and simply convert it from Keras to OpenNX. If you don't know what is the OpenNX, that's a lightweight framework to run inference on different machines. So when I have this OpenNX model, it's pretty simple to run inference. I don't need any TensorFlow, Keras, Torch, or anything. And I can run this on low-end devices. It is optimized and runs usually faster than the original model. It depends on the architecture. So that's enough about that. Let's go to FaceNet. And here is several options that we run this on GPU, on CPU. It's up to us. We load the anchors. This is the normalized. It's specific to FaceNet normalization. We use L2 normalized. This is for normalization for our encoders. There's detect save faces. There's a specific function that we'll use to create an anchor face if we don't have anything. Because as you saw, I have a faces here, but I don't have faces folder here. So we'll come to this in a second. And next, here is a load anchors that we load these anchors from faces folder. And there is an encode script that's one of the most important here, but let's continue within the call. So here is the call. We give it a frame. It might be image, video frame, web camera, stream frame. It doesn't matter. It should contain faces. So then I run this detector on these faces, and I return the top, left, bottom, right coordinates. That's the idea here. And then I crop these faces from the original frame, and I encode these faces. And we receive these face encodings. And then we run the cosine distance between our anchors Right now I will have 1 anchor, but we can have 10 anchors, 20, even 100 anchors to recognize the people who came to our camera. That's it. And we check the distance threshold and we pick the maximums. Okay, that's it. And here is a simple drawing function that will draw the rectangle and add the name of the face in a faces folder, of course. And the cosine distance. I'm not covering Euclidean distance because it's not that popular as the cosine distance, but it's up to you. It depends on the case. We can test usually either cosine and Euclidean distance. Okay, let's run this. I open this. As he said, this is line specifically for creating my first face because I don't have any faces, anchors, and etc. But as he said, to run this kind of face recognizer, I need to have these faces. So let's do this. And here is segmentation model. And right now I want simply to background instead of making it white. And let's run this script. It should load in a second and everything should be cool. As you can see, my first crop was saved here. I can open it. I go to the face and oh damn, it's really light. But still, it recognizes me just fine. Yeah, okay, let's close this. Yeah, it's really light, but doesn't matter. Right now I can comment this kind of script and I'll rename this to me as Rokas. That's cool. And let's run it again. It needs some time to initialize this MediaPipe face detector and etc. And as you can see, it runs 60-80 frames per second and it's pretty quick related what we wanted to achieve. And I should mention that we are running everything on CPU, so you can imagine that it's pretty nice how it works. And yeah, we are using it close to real-time stream. There's of course ways to improve the accuracy, improve the speed and etc. But I don't know if you need it. You can pick this implementation, use it on your Raspberry Pi, and you'll see that it should achieve 10 frames per second, and it's pretty enough to use this implementation as, for example, your intelligent lock, for example, on your home, where you want to unlock some kind of doors when you come, only you come. This is one of the best solutions. Also, I'm not recommending to use this as a security system for your real-time solutions, because if you would pick some kind of image, for example, of yourself, and you would be recognized your face as Rokas, for example, my picture, and you show it. Yeah, it's not a real person. If, for example, someone wants to rob your house and doors unlock with face recognition, no, it will not work. You need to some kind of estimate if it's a real person, for example, that your eyes are moving, face is moving around to left or right. It's up to you. There's a lot of more implementations how you can improve it, but at least that's somewhere where you can start. Of course, you can use this as an alarm system on your door. For example, when someone comes here to your door, your faces will be detected and you'll receive some kind of notification about who's there. You can record the stream of that face who's walking around. It's up to you. There's a lot of solutions where you can use this face recognition, and it is used nowadays. So let's close this. I wanted to show you this kind of cool implementation of all this stuff. I found this kind of face recognition. It's pretty old. There's a lot of solutions implemented, but it's still fascinating and exciting to test because, well, it's always fun and exciting fun to try these things out, how they work by your own hands, by your own implementation, or etc. Of course, you can continue to porting this to your mobile application, or whenever you want to run in a cloud, on a server, it's up to you. And I think that is enough for this tutorial. I hope you liked this video, and you can smash the like button if you liked it, if you watched it until the end. You can subscribe to my channel, share with the video, you can comment, ask any questions you want, or even suggestions. You can, of course, clone my GitHub repository, use it whenever you want, and you can update it, upgrade, improve it. It's up to you. And I do these things for free, just for fun, for learning purposes. So thank you again for watching until the end, and I hope it was useful for you, and we'll see in a next tutorial. I'll try something another exciting and interesting, continuing this tutorial series. So thank you and goodbye, my friends.